Alright, so we are going to talk about the contraction principle, sometimes called the contraction mapping principle, I believe. So this is really important in mathematics in general because there are a lot of areas of math where we have a particular function and we want to find a fixed point of that function. Basically meaning that if you have a function defined on a space, you want to see if there is a point in that space such that the function evaluated at that point gives you back that point. And so let's go ahead and start going through this. So in terms of background, this theorem that I'm going through, I'm basically just going through Walter Rudin's textbook, Principles of Mathematical Analysis, and I'm just sort of adding in a few details. And also in terms of background needed, you need to know the basic definitions of metric spaces. You don't need to know much about them. Even if you just have the basic assumptions, then even if you just know the basic assumptions and haven't learned too many theorems about them, you should be fine. But it is important to know about them, I think, just because metric spaces are really useful, because those are basically sets on which we have sort of what we would imagine a distance function to look like. And let's see what else. You also need to know some results about continuity, and that can all be found much earlier on in this textbook. But yeah, so let's go along with this and start going through this. So we just start with the definition. So if we have a metric space X and a metric D, then if we have a function phi, which it's a map from X into X, and if there is some number less than 1 such that the distance between, so for any x and y in our space, the distance between phi x and phi y is less than or equal to this constant times the distance between x and y. If this is true for any two x and y in your space, then phi is said to be a contraction of x into x. So, of course, here it says the number c must be strictly less than 1. Generally, c will be strictly between 0 and 1, because if c is less than or equal to 0, then this sort of doesn't make sense. If c is less than or equal to 0, then that means that the distance between phi x and phi y is always 0. So that's not really an interesting, either your distance metric, either your metric is sort of trivial or your function is trivial. So the only real interesting case here is when c is strictly between 0 and 1. And yeah, so that's the definition. And if you think about what this is saying, basically what this is saying is that the distance between these 2 points get closer when you send them through this function phi. And so they could move to a completely different region in your overall set, but they move closer together. And how close they move together is bounded by this constant c. And so since these things are moving together under this function, that's why we call it a contraction. And you can sort of think in your head, well, if any 2 points are going to get closer together under this function phi, then maybe there's sort of like a point where like everything sort of comes together. Particularly if you were to send points through this function over and over and over again. And in fact, that's sort of how the theorem goes. But the theorem is that if x is a complete metric space, and if phi is a contraction of x into x, then there exists one and only one x such that phi of x equals x. So the fact that phi of x equals x, that means we call x a fixed point. And the fact that there is one and only one such point means that it's unique. So yeah, that's exactly what it says. In other words, phi has a unique fixed points. The uniqueness is easy to see because if you have two fixed points, x and y, then the distance between x and y, well, since x equals phi of x and y equals phi of y, the distance between x and y is equal to the distance between phi x and phi y, and since phi is a contraction, this distance is less than or equal to c times the distance between x and y. So the distance between x and y is less than or equal to c times the distance between x and y, and since c is a number which is strictly less than 1, this can only be true if the distance between x and y is 0. Because otherwise you're saying that some positive number is less than or equal to this positive number times a constant which is strictly less than 1, which can't happen. Alright, so the uniqueness is pretty straightforward. The existence is the essential part of the theorem, which is more interesting. It's not too long of a proof. And this is actually cool. It actually gives you a method for locating this fixed point. So a lot of times when you're trying, these types of theorems where you're trying to prove existence and uniqueness of something, sometimes you can prove that, but you have no idea how you would figure out this fixed point. Or if you're trying to prove existence and uniqueness of something, you don't get a formula for how to find it. This happens a lot with nonlinear differential equations. Oftentimes you have, or like partial differential equations, these types of things. A lot of times mathematicians, you want to prove that your problem has a unique solution, but this proof doesn't always give you a way of easily finding the function. You'll usually find some properties of the solution, but you don't have like a closed, it doesn't give you an algorithm to find what this thing that you're looking for looks like. But this particular theorem gives us an algorithm for finding this fixed point. And so you can sort of think about like if you take x and y and you feed them through phi, they'll get closer, and you feed them through phi again, they get closer, and they'll get closer and closer and closer. So you can imagine maybe they'd be approaching this fixed point. And so you can imagine maybe, well, if we did that with just a particular x naught, and we just send it through this function phi repeatedly, then maybe it should go to this fixed point, and that happens to be the case. So you pick x naught in the set x arbitrarily, and you define the sequence recursively by setting xn plus 1 to be phi of xn. So you have x0, then phi of x0, then phi of x0, etc., etc. Alright, so now this is a little bit strangely worded. It says choose c less than 1 so that 43 holds. I think it's more, since phi is a contraction, c is already sort of given to you. Since phi is a contraction, we know that such a c exists, so you just use such a c. Although, I guess the definition says there exists a number c such that this holds, and there's presumably multiple c's. Well, actually, that really has to be the case, because if the contraction definition holds for c, then it will hold for any c0, which is strictly between c and 1. But anyway, so just choose some c's so that it holds. Then if you have any n needs to be greater than or equal to 1, because the index we have a x sub n minus 1, and that can't be less than 0. So we need n to be greater than or equal to 1. Then we have the distance between xn plus 1 and xn. Well, xn plus 1 is by definition phi of xn, and xn is by definition phi of xn minus 1. And then since phi is a contraction, this is less than or equal to c times the distance between xn and xn minus 1. All right, and so if you use induction, then the distance between xn plus 1 and xn is going to be less than or equal to c to the n times the distance between x0 and x1. And that sort of makes sense because every time you increase the indices by 1, the bound increases. For this inequality, you get another factor of c. So if you really want to see, so basically what Rudin is telling you here is that he's telling you you can use an induction proof to prove this, and then it's up to you to either you can eyeball it and see like, oh, that sort of makes sense, or you can actually do the proof yourself. Some ways to see that are here. So basically the distance between xn plus 1 and xn is less than or equal to c times the distance between xn and xn minus 1, which is less than or equal to c squared times the distance between xn minus 1, xn minus 2. We're just using this previous fact over and over. And if you imagine, so if we start at c times the distance between xn and xn minus 1, how many more times do we need to apply the previous inequality, and how many more factors of c do we need to add in to get to the distance between x1 and x0? Well, we need to get from xn to x1, so that index needs to decrease n minus 1 times, which means that you need to apply the inequality n minus 1 times. And so you'll get n minus 1 additional factors of c out front. And here we already have a factor of c. So we add that one factor of c to the additional n minus 1 factors of c, and that's how we get n factors of c. So that's one way of seeing it. Or you could just do the actual induction argument. The base case is the distance between x2 and x1 is less than or equal to c to the power of 1, which is just c, times the distance between x1 and x0. That's just applying that fact above. And then the induction case, if we assume that the distance between xn plus 1 and xn is less than or equal to c to the n times the distance between x1 and x0, then if we look at the distance between xn plus 2 and xn plus 1, well, we first apply that above fact, and we get that that's less than or equal to c times the distance between xn plus 1 and xn. And then we apply the inductive hypothesis to the distance between xn plus 1 and xn, and that gives us that factor being less than or equal to c to the n times the distance between x1 and x0, and we multiply that c to the n by the additional c that we have out front there, and we get c to the n plus 1 times the distance between x1 and x0. So whatever makes most sense to you, it doesn't really matter, but at this point it should be very clear that this inequality holds. So from here, we move on. Now, let's move this to here. Because after this, the textbook talks about the inverse function theorem, which we're not going to talk about. So, if n is strictly less than m, it follows that some inequality. And basically what we're getting at is we're proving that this sequence is a Cauchy sequence. All right, so the distance, so let's go through this. The distance between xn and xm, and by the way, ignore the calculations at the top for now. So this is less than or equal to the sum from n plus 1 to m of the distance between xi and xi plus I minus 1. And this is just applying the triangle inequality over and over and over again. You apply it how many times? Like m minus n minus 1 times or something like that. But yeah, so this first inequality is just a triangle inequality being done over and over again. Because the distance between xn and xm is less than or equal to the distance between, yeah, you can work that out for yourself. Okay, so now the distance between xi and xi minus 1, we apply the previous fact that we just proved to show that each of these is less than or equal to c to the I minus 1 times the distance between That should be the distance between x1 and x0. So the distance between x1 and x0. All right. So that's that. And of course, we still have this sum from I equals n plus 1 to m. And so what we can do now is we can factor out the distance between x1 and x0 because that's a factor of all of these terms. And what we're left over with is this sum, which we write out as c to the n plus c to the n plus 1 plus all the way up to c to the m minus 1. And now for the next step in the inequality, there's sort of an algebraic trick here. And that is that, well, first of all, we factor out the c to the n here. And we can see that that comes out at the very right-hand side at the end of this inequality. But then what we're left with is we get 1 plus c squared plus blah, 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 plus all the way up to c to the, what would be m minus n minus 1. And this, we're claiming here, is less than or equal to 1 minus c to the power of minus 1, or 1 divided by 1 minus c. And that's not immediately obvious, but since that's obviously the inequality that they're claiming, let's verify that that's actually true. So that's what I did above here. So if we take 1 plus c plus all the, so for any k, if we take 1 plus c squared plus all the way up to c to the k, and we multiply by 1 minus c, then we multiply through by the 1 and we get sum from 1 to c to the k, and then we multiply 1 through c to the k times minus c, and we get minus c squared minus blah 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 all the way up to minus c to the k plus 1, and a bunch of these terms will cancel out, and what we'll be left with is 1 minus c to the k plus 1. And c is a value which is less than 1. And so if you raise it to this power, then that's also going to give you a value which is less than 1. And so this, what we end up with is strictly is going to be less than or equal to 1. Now this is actually interesting. I'm now thinking about this. Does this still work if c is negative? I don't know if this still works if c is negative. It might, but I haven't really thought about it. So basically just, I mean, this, we're not really going to be using this theorem if c is negative, like it's not really interesting, so just, I don't know, I wouldn't worry about that. Because like I said before, if c is negative, then the contraction mapping, something's trivial. Either the metric is trivial or the contraction is trivial. Well, wait a minute. Actually, what if the contraction is trivial? If the contraction is trivial, that means, so the distance between any, that means that everything is sent to a single point. Okay, so yeah, it still holds. If the contraction is trivial, then basically the function sends every point to a single value. Let's say phi of x equals y for all x in the space, and then y is your fixed point. Okay, so it still works if c is 0. But if c is negative, there might be some issues here, but I won't worry about it. Anyways, okay, we're getting off track. The important thing is c is between 0 and 1. That's the important case here. So, let's see here. So, we have that the sum from 1 to c to the k times 1 minus c is less than or equal to 1, so you just divide both sides by 1 minus c, which you're not dividing by 0 since c is less than 1. And so you get the inequality 1 plus c plus all the way up to c to the k is going to be less than or equal to 1 over 1 minus c. And so that's the exact inequality that we're using in this final step here. So the distance between nx and the distance between xn and xm, wow, is less than or equal to this thing here, 1 over 1 minus c times the distance between x1 and x0. That's a constant, so I'm just going to call that constant m. So the distance is less than or equal to this constant m times c to the n. And of course, this c is a constant, which is less than 1, and n is not fixed. But this confirms that the sequence of xn's is a Cauchy sequence. Remember, what that means is that given an epsilon, we need to choose a capital N large enough so that for all n greater than or equal to capital N, the distance between... We need to choose a capital N such that for all n and m greater than or equal to capital N, the distance between xn and xm is less than epsilon. And so if we choose, so what we need to choose here is we need to choose capital N, given an epsilon, we need to choose capital N large enough so that for any n greater than or equal to capital N, capital M times c to the n is less than epsilon. And this is certainly, and this has to hold for all n greater than or equal to capital N. And this is certainly possible since m is just a positive constant and c is a positive constant, again, I'm just sticking with this, positive constant between 0 and 1. And that means that if you multiply it by itself, it gets smaller and closer to 0. So you can basically multiply it by itself enough to ensure that c to the n is less than epsilon, and then if you were to raise c to a higher power, then you'd get something even smaller. And so this would hold for all n greater than or equal to capital N. And so if you choose capital N in this way, then the distance between xn and xm is less than or equal to capital M times c to the n, which is less than epsilon. And that's what you need. That's the definition for a sequence being Cauchy. So the sequence of xn's is a Cauchy sequence. And now we use the fact that x is complete because this Cauchy sequence needs to converge to something in the space. And that's only guaranteed if x is complete. But since we assume x is complete, the limit of the xn's exists and is equal to x for some x in the space. And so this is our candidate that we end up with for the fixed point. And to prove that it actually is a fixed point, now what we do is we note that since phi is a contraction, phi is continuous, and in fact it's uniformly continuous. And if you want to prove this, you need to use you can use the delta epsilon definition, and setting epsilon equal to delta suffices. Because so for any x and y in our space X, if the distance between x and y is less than or equal to delta, then the distance between phi of x and phi of y is less than or equal to c times delta. And c is less than 1, and delta is equal to epsilon, so c times delta is strictly less than epsilon. And so there we go. That proves that phi is uniformly continuous. But all we really need here is continuity, because what we do is we take, well, phi of x is equal to phi of the limit as n goes to infinity of xn. And what we need to do is we need to take this limit outside. And continuity allows us to do that. So by continuity, phi of the limit as n goes to infinity of xn is equal to the limit as n goes to infinity of phi of xn. And now phi of xn is xn plus 1 by the definition of our sequence. So this limit is equal to the limit, the limit as n goes to infinity of phi of xn is equal to the limit as n goes to infinity of xn plus 1, which we know is equal to x. And so phi of x equals x. And so x is a fixed point. So we've proven that we have a fixed point, and we already know it's unique. So hence there is a unique fixed point. And so furthermore, this actually shows us how to approximate this fixed point. This doesn't give us a formula for our fixed point exactly, but it shows us how to approximate it. You just start with any point in the space that you want, and you just send it through phi, and you do that over and over and over and over again. And if you do that enough, you'll get closer and closer and closer to the fixed point. And so that's how you go about finding the fixed point. And so that finishes the theorem that we were trying to prove. And yeah, like I said, this is a really important concept in mathematics. And the main thing here is that typically when we think about metric spaces, the standard example that we'll think of is maybe like R or like RD. So just like a d-dimensional real vector space. But we're not restricted to that. This can hold for any vector space. Or no, for this can hold for any for any metric space. So for any metric space, if we have a contraction on any metric space, then we have a unique fixed point. And so you can consider much more complicated metric spaces than just RD. And this can be really useful in some cases. Like, for example, let's say, so here I'm just going to write an example. Let's consider functions like this. Let's say we have a differential equation. X prime equals f of x. And here, x is a point in RD. So basically what we're doing here is we're considering no. X is a function X is a function of, we might call it a function of t. And so it's a function, you plug in a t value and you get a point in RD. So we're looking at functions like this, and we're looking for a solution to this differential equation, f prime equals f of x. And so what we do is, or what we want to do is we want to know, well, does this equation have a solution, and is that solution unique? And if this function f is really weird, then we don't know. But if we put some restrictions on the types of functions x that we're looking for, and if we put some restrictions on the types of functions f that we see here, like for example, if we say that f has to be Lipschitz continuous. You can learn about all of this stuff if you dive into this deeper. But the main point is, so what we're looking for is we're looking for a function from R to RD. And so you can think about this as we're looking for a point in a space of functions. And so one thing that we can do to prove that there is a solution to this equation is under some circumstances, we can actually define a space of functions and define an operator on this function space in such a way that a function satisfies the differential equation if the function is a fixed point of this operator. And of course, this operator needs to sort of be in a... So this operator is a function which takes in functions and spits out functions. And this function space that we're looking at, we can put a metric on it. We can put a metric on it that turns it into a complete metric space. And under some conditions, these operators, this operator that I'm describing, which has a fixed point whenever the function that you're plugging in satisfies this differential equation, this operator itself, you can prove, is a contraction. And then you apply the contraction mapping theorem to prove that there is a unique fixed point. And this unique fixed point of this operator corresponds with a unique function which satisfies this differential equation. And so not only is this theorem really neat, but it's really useful in a lot of other areas of mathematics. And even in this textbook alone, the reason that they bring up this theorem here is that they use it to prove the inverse function theorem, which is like, I think it comes right after this in the textbook. But yeah, so this is a really neat theorem. You don't need a lot of background to understand it, and it's also really useful. And it's also sort of explicit in that it shows you how to approximate the thing that you're looking for. It shows that a fixed point exists and is unique, and it shows you how to find it. And for those reasons, I think this is a really important theorem in mathematics, and that's why I wanted to discuss it. And that's about all of the things I wanted to discuss about this theorem. And so there you go. Now you understand the contraction mapping theorem.